The title of this lecture is Sound. Now, I'm not a physics teacher, and so there's a lot more a physics teacher could tell you about sound than I can. I'm just going to tell you about sound from the perspective of the human body, trying to interpret it. So, in order to sense sound, we must have the ability to detect and interpret sound waves. Now, sound travels and light travels, but there's a huge difference between the two. Light is a type of electromagnetic radiation. It travels in this sort of wave form, and the distance between these sort of waves that do this kind of sine wave pattern would determine what type of radiation it is. Visible light, for example, has a certain distance between the two. A little further apart from the waves would be infrared. A little further apart in those waves, and you'd be dealing with radio waves. Closer together, ultraviolet. Closer than that, X-rays. Things like that. There's a few in between I probably missed, but this doesn't really require a medium to travel through. Light travels through space. And space is quite literally space. There is nothing. There's very few air molecules. There's dust particles. There's stars and planets and stuff. But most of space is just quite literally just space. And light and all kinds of electromagnetic radiation has no trouble traveling straight through that. Sound, on the other hand, requires a medium. And for our purposes, we're going to talk about air. Now, air is just a whole bunch of moving particles, nitrogen gas and oxygen gas and argon and a few others like that. And the particles are all spread out like this. And those particles are going to be flying around, crashing into each other, so on and so forth. Now, when we send sound through the air, basically what we're doing is we are expanding and compressing those molecules in a very specific way. And it ends up looking kind of like this, where we have a collection of those things together, and then kind of an expanse in between, and then there's another collection of those molecules together. So we cause waves to form in sound, but they're traveling this direction. They're not up and down. They're going, straight across like that. There's probably a better way to phrase that. But note that these collections of air molecules that I've got, I'm drawing these roughly the same distance from one another, okay? There is a few in between, but there is this right here in between, and this is between here and here is the wavelength. But we're not particularly concerned about the wavelength of these things, because that's not really how we quantify sound waves, is how close together these things are. We quantify these with how many times do these wave type things occur in 1 second. So there's two, that would be called frequency, okay? How often they occur in a second. So I'm going to go ahead and mention the two quantifiable and there are more than this, properties of sound. Okay, they are very simply frequency, which is how many waves in 1 second. Okay? And it's measured in the same way pain is. Small, terrible joke. The unit is hertz. HRTZ. Hertz. To us, we hear this as pitch. What we understand pitch to be is how many waves in second, how many waves, or specifically cycles per second, how many cycles per second. I have an app on my phone I want to show you here. It is Pitch Lab Pro, and they may have since replaced this with another app, but it's a guitar tuner app basically. Trying to hit A at about 110 there. Now, if I hit the next octave, note that they're all perfectly double. Well, if I could hit them, they would be 110 for A, 220 for A, and then 440 for A. That's just how many cycles. Somewhere. Sorry. Anyway, so that's showing you what pitch is, frequency. Basically, how many of these collections of waves occur in a second. When I hit that high A, that meant 440 of these waves of air molecules crashing together was moving through in every single second. So it's pretty amazing. Our ear can detect that because basically our eardrum collects these waves that crash into it, and then vibrates as such. And we'll get into greater detail on what happens with those vibrations in the next video. But beyond frequency, we have something else, and that is amplitude. Basically, how big the waves are. If you think about it, you know, a pin dropping versus a firecracker exploding, you know, it could make the same pitch. Probably won't, but it could make the same pitch. But very clearly, there's going to be something different about it's not just the distance between those waves, it's the size of the waves themselves. And so we're going to measure that. That unit will be in something called decibels. And we understand it as volume. And it's very easy on your stereo in your car, you know, the volume. Turn the volume up, you're increasing the amplitude. In fact, the device that actually increases the amplitude of sound waves it's called an amplifier. Your guitar amp is an amplifier. It takes the signal and it amplifies the sound of it so that it can be heard and you know, and also make your ears bleed, make you sound like a rock star. But that's the job of this. Now, what's neat about this scale, decibel, is decibel. Okay? And what's neat about this scale is it's logarithmic. What that means is that every step is a factor of 10. So, in a nutshell, something with a decibel rating of 79 is 10 times louder than something with a decibel rating of 78. So it moves up pretty quick, which is why you don't hear about decibel ratings much more than about 160. That's like standing on a rocket pad, a rocket launch pad, assuming that you don't get engulfed in flames and stuff. If your ears can survive it, if you can survive it, but yeah, depending on the decibel rating of whatever it is, chainsaws and things like that, you need to wear ear protection because prolonged exposure to loud sounds, including if you're wearing headphones while you're listening to my voice right now. Hopefully you've got them at a reasonable level, because listening to loud music in headphones and things like that can also have that kind of impact. So, in a nutshell, going back over this again, sound. In order for our ears to be able to detect sound, we have to gather it. Like our eyes are able to gather this type of radiation, which is you know, visible light. Our ears have to gather this sort of waveform, which moves in compression, basically compression and expansion of air molecules that waves come in. However far apart these waves are, moreover how frequently they arrive, which is why it's called frequency, how many cycles in a second, that's how many hertz it is, how many cycles per second. Oh, and I should mention, the absolute limit for what we can hear is between 20 and 20,000 hertz. Okay, that doesn't mean that you can hear 20,000 hertz. A dog can, but you probably can't. But maybe 17,000, somewhere in that range. And that doesn't mean that you can hear all the way down to 20 either. But this is the absolute limit for human hearing. And then amplitude, how big the waves are, how loud something is, or volume is measured in decibels. And that should just about do it for our intro to sound, to get us into then how the ear is able to collect that sound.